Bit reduction or bit crushing is a type of distortion where we process an input signal such that our output signal only has certain possible amplitude levels. This type of distortion simulates the process of converting an analog signal to a digital signal. We quantize or round off the amplitude levels to certain numerical values. Keep in mind, when we're performing this effect, we don't actually have to change the bit depth of the files storing our signal on our computer. In Matlab, we can choose from a few different rounding functions. However, they all have the same limitation that they'll round a signal or a number off to the nearest integer. When we're working with a signal within a range of -1 to 1, it will round the signal off to just a few values, -1, 0, or 1. A trick that we can play to perform bit reduction for a certain number, an arbitrary number of amplitude levels, is to temporarily stretch our signal out over a larger number of integers, round the signal off to those values, and then decrease the amplitude back to fit within a range of -1 to 1. So let's look at in Matlab how we can create our own bit reduction function. Let's go through a demonstration step by step to look at how we can process our input signal to perform bit reduction. I'm going to make use of this script we created previously to test the different distortion functions. Initially, I'll start out by writing some commands within this script that will demonstrate the concept of how bit reduction is going to work. Then I'll move some of those commands over to its own function M file. First, let me comment out some of these commands that we had when we were looking at a different type of distortion. What we like to do here is take our input signal that's a sine wave, a smooth curve that spans a range from -1 to 1. Let's process it. So we create an output signal that just has a few possible amplitude levels. So I'm going to make use of a built-in Matlab function called round. Take our input signal as an argument. I'll run this script. We can plot the input compared to the output. So our input signal is in blue. It's a smooth sine wave curve. And our output signal is the distorted red signal. The round function is going to round towards the nearest integer. So when our blue signal has any amplitude from 0 up to 0.5, our output has a value of just 0. When we're within a range of 0.5 up to 1, we're going to round it up to the integer of 1. Same thing when we look at negative numbers. When our input signal is 0 down to -0.5, it gets rounded up to 0. And then when we have -0.5 down to -1, our output signal has a value of -1. So in this case, we've produced a signal that really just has 3 possible amplitude levels. We're getting closer to the concept of what bit reduction is all about. Now, this is one possible rounding function that we can use. And actually, for our purpose, it's one that's not very good. And it's more intuitive for us to work with a different function. And that's because the rounding function sometimes round things up and sometimes rounds things down. So it's difficult to kind of pinpoint exactly what number of amplitude levels we have, or what's the relationship ultimately between some number of bits that we like to have and the number of output amplitudes. So let's switch over. Instead of using round, let's use another function, ceiling. It's going to round things up. So we're always rounding up to the nearest integer. As soon as our input signal has a value that's greater than 0, it's going to round it up to 1. It doesn't matter if that amplitude is 0.1 or 0.9. Always gets rounded up to the integer of 1. Then when we're within the range of 0 down to -1, we're going to round it towards 0. There is this exception though, when our input signal actually has an amplitude of -1. For our purpose, we're going to ignore this when we think about the number of possible amplitude levels there are. We're going to think about our input signal, making sure that it stays within this range of -1 to 1, and that it's very rarely actually going to have this amplitude. So for us, this kind of processing with our ceiling function will produce a signal that has 2 amplitude levels, 0 and 1. This is equivalent to what happens when we work with 1-bit audio. 1 bit can either have 0 or 1, and that's 2 amplitude levels. There is also a different function that would perform a similar kind of thing. That's the floor function. Actually gives us we're thinking about the concept of bit reduction, the equivalent kind of thing, except it's 0 and -1. There's this special case here when it has the actual value of 1. But for me, I prefer to work with this ceiling function that rounds things up. So we have the situation that comes up with any of these built-in functions that they will only round to integers, that we can't tell it that we like to round to a fractional number. And so we have to think about doing some additional processing in order to accomplish that. We like to be able to create some distorted output signal here in red that doesn't just take on integer values. Maybe it has values of 0, 0.5, and 1, and negative 0.5. That would be 4 possible levels. So let's think about how we can go through some additional steps to make that possible. So let's look at what would happen here if we were to take our input signal and instead of having it fit within a range of -1 to 1, let's stretch it out. So I'm going to multiply it here by 2. So when I multiply by 2, our input signal now obviously goes within a range of -2 to +2. Then when we go through the process of rounding the signal off using the ceiling function, we have more integers to work with. We have 0, 1, 2, and -1. So we have 4 possible amplitude levels that we're getting for our output signal. And that's great. However, our signal now is going outside of the range that's acceptable for audio. Audio, we still need our output signal to fit within the range of 1 and -1. So instead, let's go through a 2-step process where we take our input signal, that's a sine wave. We're going to do the same equivalent thing by multiplying by 2 down here for our ceiling function. So we'll still stretch our input signal out, then round it off, and then let's add an extra step to shrink it back down within the range. To perform the inverse of multiplying by 2, we can multiply by 1 divided by 2, or 0.5. Now when we run this script, we're going to take our input signal, stretch it out, round it off, and then shrink it back down. So our output signal now fits within the range that we need from -1 to 1, and we're also then accomplishing 4 amplitude levels in our output signal. 4 amplitude levels is equivalent to 2 bits of audio. There's 4 combinations of zeros and ones that you can put together to create 4 possible levels. So let's do this for a higher number. How about 4? Let's stretch it out over 4 numbers and then shrink it back down. Look at the result. So in this case, we're going to accomplish a lot more amplitude levels. In fact, we can count them up. 1, 2, 3, 4, 5, 6, 7, and 8. We get 8 levels. We multiply our signal here by 4. We could continue on looking at this pattern. Actually, it's helpful to go up by powers of 2. Trying to think about this. So now we actually have 16 possible amplitude levels. So we have to keep all these different things straight. The number of amplitude levels, what kind of scaling we need to do to our input signal to achieve those input levels, and think about, well, what's the equivalent then in terms of the number of bits? When it comes to bit reduction processing, a lot of times we want to be able to say, we'd like to have 2 bits. We'd like to have 4 bits, 8 bits, 16 bits, and make sure that our output signal has the appropriate number of levels. So the relationship here, if I want to demonstrate this, let's go back to what we had initially. So if I multiply here by 2, what does this look like? We stretch things out. We get 4 amplitude levels, which is the same thing as 2 bits. So our number of bits, think about amplitude in terms of 2 raised to the power of the number of bits. Now, because we're working with signals that are actually stretched over a larger range, stretched over a range of -2 up to +2, that's over 4 integers there, then we're actually getting the number of bits. So number of bits is going to be 2. So we're stretching it out, and our amplitude scalar then is going to be 2 raised to the power of the number of bits minus 1. So if our number of bits is 2, 2 minus 1 is 1. 2 raised to the power of 1 is 2. Let's look at then happens if we go up to 4? What happens there? So we're going to get 8 possible amplitude levels. So 2 raised to the power of 4 minus 1, so that's 3. 2 raised to the power of 3, that's going to give us 8. So now we have our relationship between the number of bits and how much we need to stretch out our signal across the appropriate number of integers or amplitude values in order to perform the processing. So let's move some of this code over to a new function that will perform this type of distortion for us. Let's write a new M file called function. Has an output argument of our output signal. Then we're going to have a function name called bit reduction that will take our input signal as an argument and also some number of bits. So we could say 2 bits, 4 bits, 6 bits, however many we want. Okay, so here we're going to perform bit reduction, or also called bit crushing. So I am going to say that just as a good habit to get into, we don't necessarily have to do it in this case, but let's go over sample by sample of our signal and process it. Some of these rounding functions can actually take in the entire signal and work with them, but for us, I think it's intuitive to be thinking about go through each sample of our signal and process it separately. So that's what we'll have this loop for. But we have to calculate a few things before this loop. Let's calculate and determine what we're going to scale the amplitude by. We're going to increase it, stretch it over some number of integers to work with. So determine the desired number of possible amplitude values. So this is going to be based on the number of bits that come in. We looked at this. Say amplitude values that we want is 2 raised to the power of our in bits minus 1. We can double check that this works later on, but if we put in, 2 bits here, it's going to be 2 raised to the power of 1. Put in 3 bits, it's going to be 2 raised to the power of 2, and so on. So that will be good. Then we actually need to process our signal. So we'll go in here. We'll say that our output signal for this sample number n is going to be equal to our ceiling function, where then we're going to multiply that by the amplitude values multiplied by our input signal at that time value, and then multiplied by 1 divided by our amplitude values. Now, if you wanted to break this up into separate steps, you could do that, or you could just write one line of code that essentially does what we had before in our distortion test script. So let me save this file. It's bit reduction. Then we should be able to go back over here, these things, call this function. Now I'm going to put in some number of bits here. Let's put in, how about 1 bit to begin with? Let's see if we're getting an output signal, what we would expect, plotting the input compared to the output. So here we've got 2 amplitude levels. We can increase this 2 bits. It's 4 amplitude levels. 3 bits. That's 8 amplitude levels, and so on. You can see that as we increase the number of bits, about 8 bits, we get a lot more amplitude levels, even to the point that it's hard to see this stair step actually happening. I could zoom in. It'd be easier to see some of this happening. Another nice thing about this is it allows us to actually put in some number of fractions of a bit. Now, when you're working with real physical converters, you can't really have a converter that does a fraction of a bit, but it's not uncommon in audio plugins to be able to adjust some knob that allows us to do like 2.5 bits. But really what's happening here is we're just putting in some number here in terms of the number of amplitude levels, scaling our signal up by that, and then shrinking it back down. So if we wanted to, it's possible for us to do this fraction of a bit, just like you'd find in audio plugins. So we're able to get more possible amplitude levels. But for us, let's just stick with an integer. How about 3? You can see that we're getting the appropriate number of amplitude levels in our output based on some parameter or number of bits. So there are several different steps that we can use to create the bit reduction or bit crushing audio effect.